Hello, this is a video which is going to explain how to solve the one-dimensional heat diffusion equation for a finite rod. And I've already got a video where I derived the one-dimensional heat diffusion equation, so if you haven't watched that, you should go watch that first. So, what we mean by a finite rod is that it has a starting point and an ending point. And the starting point is at x equals 0, and the ending point is at some arbitrary length L. So the ending point is at x equals L. And we're going to say that the initial temperature of the rod is at T0. So T0 the initial temperature of the rod is at T0, so the rod is uniform in that temperature. But at some time T, we immediately raise each end of the rod to a temperature T1. And so when we immediately raise the temperature of the rod from T0 to T1, we will get a temperature gradient, and as we know, heat flows across the temperature gradient. And so what we'll get is a heat flux down the rod. And this heat flux will essentially change, well, the heat flux will remain constant because we've immediately raised the temperature of the rod, but the heat will accumulate inside of the rod. So the rod will eventually reach the final temperature, which is when the whole rod has another uniform temperature, T1. So if the whole rod starts at T0 and we immediately raise the temperature from T0 to T1, the temperature profile of the rod is going to change over time. And the point of solving the one-dimensional heat diffusion equation is to find that temperature profile change over time. So I'll start off by rewriting the heat diffusion equation that we know and we derived last video. So that's d2t by dx squared times by the heat diffusivity alpha is equal to dt by dt time. And what we're going to do is we're going to use something called non-dimensional variables, and I'm going to put up a video where I explain how to derive these non-dimensional variables, but for now you'll have to take my word for it that T hat equals the temperature T minus the temperature T1, which is the temperature when we raise the temperature of the surface, over T0, the initial temperature, minus T1. That's our non-dimensional time. Now we're going to define a non-dimensional length, which is pretty obvious. It's just going to be some z is equal to x over L. So now we're going to define a non-dimensional time, which we're going to call tau. And tau is equal to alpha over L squared times t. So what can we see from these non-dimensional variables? Well, we're going to see that when we're at time equals 0 and the surface temperature is at T0, T is going to be equal to T0, so we're going to have T0 minus T1 over T0 minus T1, which is equal to 1. And that's going to be at T time equals 0. When time equals 0, tau equals 0. And when time goes to infinity, tau goes to infinity. We're also going to see that when you're at x equals 0, z equals 0. And when you're at x equals L, z equals 1. So what we can do now is we can write some boundary conditions. So what we need to do is, because we have this equation which is second derivative in x, or second order in x, and first order in time, that means we need two boundary conditions and one initial condition, or two spatial boundary conditions and one temporal boundary condition. So what I'm going to do is I'm going to rewrite the heat diffusion equation in terms of non-dimensional variables, and I'll show you how to do that in a different video, but for now take my word for it that it's going to equal this. So you can see that the alpha term, the heat diffusivity, has dropped out of the equation, and is no longer, it's contained within tau, the non-dimensional time. So let's write some boundary conditions. So we know that at time equals 0, the rod is uniform in temperature at T0. And then at time greater than 0, we instantly raise the temperature of the sides of the rod, which go to T1. So let's start with our time or our temporal boundary condition. At tau equals 0, that's going to have the effect that T hat equals 1. And at tau greater than 0, we're going to have two spatial boundary conditions, and the first one is going to be at z equals 0, which is one end of the rod, and we said that T hat is going to equal 0. So why is T hat equaling 0? Why is T hat going to equal 0 at z equals 0? Well, that's because when we instantly raise the temperature, we're instantly raising the temperature to T1. So we get T1 on the numerator, and T1 minus T1 on the numerator is 0. And 0 divided by T0 minus T1 is also 0. So at z equals 0, T hat equals 0 for any tau or time greater than 0. And the same thing applies for z equals 1, the end of the rod. We're also going to get T hat equals 0. So here we've got our time condition and our spatial condition. Now that we've defined these, we're ready to start to solve this differential equation. So the method that we're going to use to solve this differential equation excuse me, is called separation of variables. Separation of variables basically means that we're going to separate out this differential equation, and we're going to say that a solution exists for t hat, and that it's going to be a product of a function only in z and a function only in tau. So that doesn't make much sense. I'll show you what I mean. We're looking for a solution for t hat in z and tau. So this is a solution for temperature in space and time, and we're looking for a function that is a solution for this, and this is a solution for this second order differential equation. And the solution that we're going to guess exists is a solution of the form some function beta of z multiplied by some function theta of tau. So what we've done here is we've said that a solution exists for t hat, which is a function of z, and tau, which is a product of two functions, each of which are only a function of z and tau. So we're saying that we're assuming that this solution exists. Right, so how can we show that this solution exists? And if the solution does exist, what can we do to prove it? Well, we can substitute this into this equation. So we've got the left hand side and the right hand side. So if we substitute this equation that we said is a solution into the left hand side, we're going to get this. So remember, t hat, which occurs here, also occurs here, and the left hand side is essentially differentiating t hat twice. So if we differentiate t hat twice, what we'll get, we'll apply the product rule, and what you'll see is we'll get the second derivative of beta with respect to z multiplied by this function theta plus the second derivative of theta with respect to z multiplied by this function beta. And what you'll see is that because theta is not a function of z, this term will be 0. So the left hand side is equal to, I'm going to use shorthand notation for the derivatives. I'm going to say it's equal to beta prime prime times by theta. And what you'll see is, what I've done is that I've actually not shown that beta is a function only of z and that theta is a function of tau. You'll just have to, it's just implied that beta is only a function of z and theta is only a function of tau. So when I say beta prime prime, what I'm saying is beta, the second derivative of beta with respect to z, beta prime prime, is this. So that's the left hand side of the equation sorted. Let's consider the right hand side of the equation. The right hand side of the equation is oh, excuse me, I missed a t hat there, is dt hat by dt time. So if we take this solution, t hat, and we differentiate it once with respect to t, or tau is what I should write, what we'll get is, again by applying the product rule, is we'll get d beta by d tau multiplied by theta tau plus d theta by d tau multiplied by beta, which is a function of z. And again, you'll notice that because we've differentiated here beta with respect to tau, and we know that beta is not a function of tau, that this term must be 0. So what we're left with is the right hand side, which is, and again I'm going to use shorthand notation, theta prime times beta. And because we know the left hand side equals the right hand side, we can group these and say beta prime prime of theta equals theta prime of beta. And what I'm going to do now, so I'm just going to collect betas on one side and thetas on the other side. So what this will show is that beta prime prime over beta is equal to theta prime over theta. Now, this is actually very interesting because what we're saying is that the left-hand side is only a function of z, and the right-hand side is only a function of tau. So while beta may change, while z may cause beta to change, the combination of beta prime prime and 1 over beta doesn't change. And similarly, while tau may change and theta tau may change, the combination of theta prime and theta won't change. And therefore this is equal to some constant. Right. So for reasons that I'm not going to get into, and I might get into in another video, the constant that you should choose in order to get a sensible solution which isn't trivial is that the constant equals minus some lambda squared. constant must be negative. This is important so that the general solution essentially makes sense. So I'm going to leave it for here. I'm going to leave it here for now. And in part 2, I'll go over how you actually use this constant and this form in order to solve the differential equation.